programa de fusión nuclear en Brasil, que debo decir es en realidad en Latinoamérica el único programa serio en fusión nuclear. Sí. Yeah. Okay. Yeah. Bien. So, whenever you wish to start.
All right. I suppose I have 20 minutes, right?
No, you've got about half an hour. Yeah.
Half an hour,
Yeah.
okay. So first of all, thank you, Julio, for the invitation. Even if I'm not at home, let's say I'm here in Vienna, I think this is very important to show what we are doing in Brazil, and especially today, by coincidence, we had a very long meeting discussing how TCABR and how our future national laboratory could be a point of contact for Latin America. So let me present what we have been doing in Brazil, and at the end I'll comment more on the discussions I had today here in Vienna. So first of all, let me show this this structure here. This is an overview of the structure that we have today in Brazil about the current strategy that we developed for bringing nuclear fusion back to life, let's say, in Brazil. Because in the last 20 or 30 years, for 3 decades, nuclear fusion was losing human resources without supplying new resources. And today we are in the situation that we now have the funds, let's say, from authorities, from our National Nuclear Commission, from the Ministry of Science and Technology. Now, our issue, let's say, it's not money anymore. It's people, it's human resources. So we had to come up with a way to breed again this new generation of plasma physicists and engineers. And the way we are doing this is through the upgrade of our current machines. Even though they are small machines comparatively with other machines around the world, we are using these upgrades as a platform to train a new generation of plasma physicists and engineers in technologies associated with nuclear fusion. So here I don't know if you see my mouse, probably not because I'm not seeing it. But on the top left, you see the upgrade of TCABR, which is the largest machine in Brazil. It is operated at the Institute of Physics of the University of São Paulo, where I work at. Then we have the ETE tokamak in the top center, the upgrade of ETE, which is a spherical tokamak operated at the INPE institution. And then on the top right, we have the Nova UFIS, which is an even smaller machine that is being operated in a state in Brazil called Espírito Santo, which is actually my home state. So through these 3 upgrades, we are training a new generation in collaboration with colleagues from US, Europe, and China. And we are establishing collaborations specific with these people because we also want them to help us in the design of our future tokamak, which is going to be a significantly bigger tokamak, which is going to be built and installed in this National Laboratory for Nuclear Fusion, which is in the right and middle of this picture. We are already 1 year in land preparation. It's a 2 million square meters piece of land. It's going to be a whole nuclear site where part of it is going to be dedicated for nuclear fusion. And inside this new laboratory, we're going to install a new tokamak with superconducting coils, basically high temperature superconductors. And all these collaborations with other countries is helping us to design, to start, let's say, designing this machine. We didn't start yet. We are still on bureaucracy, let's say. We are establishing the MOUs, the Memorandum of Understandings, and sending people abroad. And part of the students, part of their work while they are in these other countries will be parts of the design of this new machine. We also have a group working here on the bottom right, working on the nuclear part of a tokamak. That, I mean, how you can extract the energy from the neutron and transform it to energy, electrical energy. So this is done in these blanket modules. And we have a group of nuclear physicists and engineers working on that part. We also have laser-induced fusion. We just bought a 15 terawatts laser from a company in France. And this laser is going to be delivered in October. And with this laser, we plan to accelerate protons up to 10 MeVs of energy and use those protons to study proton-boron fusion. So laser-induced fusion is also in our roadmap. And here on the bottom left, we have a group working on development of these high-temperature superconductor coils. And all these arrows, you can see that they point to the National Program for Nuclear Fusion. And this is the national program. I'm the first author of this program. It contains the guidelines that provides a north for all those activities. And the National Fusion Network, which was created by our Ministry of Science and Technology, is the institution, let's say, or it's the organism that's going to finance all these different groups. And one very, very important thing is that you can see that, that there is one arrow going out of this and going to this technological innovation. In my opinion, this is a very important part because this is the opportunity we have to develop our industry. And there are lots of technology that can become, I heard something. Are you listening? Are you still listening?
Fine, yeah.
Oh, okay. So this technological innovation block, for example, we already have 2 startups, one focused in the HTS part, so how to design, how to build high field magnets using high temperature superconductors. We have another startup that is being created to provide these high power power supplies for controlling the plasma in a tokamak. And there are lots of applications that we could benefit from if we invest in fusion now. So it's not something that you are going to get energy in 20, 30 years. We do get benefits right now, today, with this technological innovation. Now, today I'm going to be short. I will just mention a few things here. I'm going to focus in the upgrade of the TCA machine, a small part of the NOVA UFIS upgrade, and then in the National Laboratory for Nuclear Fusion. So first of all, as I said, we have a national program for nuclear fusion. And in this document, we define short, medium, and long-term guidelines and actions that create the conditions in the country to include fusion in the future, if, of course, it becomes attractive in the future. Some people there might recognize a few names in here. For example, within the authors, we see there Ricardo Galvão, which is a familiar name for most of the ones that work in fusion. But basically, our national program was built on the top of 3 pillars. The first one is nuclear fusion in Brazil has been done in a university level. So to be really productive, we should have a national scale laboratory, because it becomes hard to work on fusion within a university laboratory. We should go to a larger place with stronger capabilities. And we propose in this document the construction of the National Laboratory for Nuclear Fusion. And we finished land preparation, and we are going to enter now the phase of construction of this new building. The second pillar, and it's very important, is to train human resources through collaborations with national groups and international groups. And the third one, as I mentioned, it was the technology innovation box. It's to get a progressive involvement with the national private sector, because at the end, we must have suppliers within the country so that the country takes advantage of these associated technologies. So these three pillars are being followed very closely by the National Fusion Network group. And for those who are interested, all the documents are in this web link here at the bottom. This is an image of the future National Nuclear Fusion Laboratory that is being implemented. As I said, we already started land preparation. Actually, it did not started this year. It started March last year. And last year, we also had this National Fusion Network created by our Ministry of Science and Technology in July 2025. Here at the bottom is you can have access to the full text of the decree. And now let me talk more about the physics. So this is the TCABR for those who are not familiar with the USP laboratory. You can see here the typical size of this machine because there is a hydrogen cylinder close by. So you can have an idea of the size of the machine. And this machine came from Switzerland. And at some point, after 20, 30 years of operation, it became clear that TCABR needed an upgrade to continue providing relevant results. And the way that we decided, and of course, this upgrade is a platform for training human resources, but we wanted to upgrade the machine to something that could be useful for, to be really useful to develop nuclear fusion. So we decided to include within the, or install within the vacuum vessel, a set of resonant magnetic perturbation coils. These coils are used to control some plasma instabilities called edge localized modes, which are modes or instabilities that occur in the plasma edge. They look like very much those plasma eruptions that you see, for example, in some, when you see people talking about this plasma ejections from the sun. In the plasma, you also see in the edge some eruptions occurring. These we call edge localized modes. And if these modes, when they erupt, there is an ejection of high temperature plasmas that can damage the walls of the machine. And we have to control these instabilities. Today, TCABR is only, it allows only circular plasmas. So you can think a donut shape, a torus with a circular cross-section. But after the upgrade, we are going to have plasmas with this typical shape here. We call this a double null or a diverted plasma because you can divert the particles to hit the upper part and the bottom part in some specific regions. We are going to increase our toroidal field from 1.1 Tesla to 1.5, and we we will be able to extend also. At the bottom here, you can see the discharge duration from today's 120 milliseconds to 2 seconds. And we are going to use for that a set of plasma guns in the bottom of the machine. Just to mention a little bit about these instabilities that we plan to control, these ELMs, and why this is a still open problem. You can see here on the left, this is a heat flux measured at the wall of a tokamak. You can see that you get usually a 20 megawatts per meter square, and then suddenly, once an ELM or a eruption occurs, you can see it jumps to above 80, or let's say about 100 megawatts per meter squared. Just to give you an idea, I know there are lots of students also hearing. Julio told me there would be students. Just to give you an idea, when you see movies of a spatial vehicle during the re-entry in our atmosphere, you see all those things shaking and warming and get hot. The heat flux associated in the re-entry of a spatial vehicle is of the order of 3 megawatts per meter square, or maximum 5 megawatts per meter square. Here we are talking about 100 megawatts per meter square during an ELM. Materials today cannot support such high heat fluxes. So there is no way materials could survive a pulse of heat like we are seeing here. And projections to larger tokamaks, like the tokamak called ITER, which is going to be the largest one and is being built in France, south of France, in a place called Cadarache. You can see that the peak heat flux in this machine called ITER can go up to about 1 gigawatt per meter square in the right figure. So there is no way that materials can survive this, and the triggering of ELMs is still considered a scientific and technological challenge. And when there is no technological solution, then we have to stop and think in a scientific solution. And that was done, that was actually tried for the first time in 2006 by Todd Evans from General Atomics in San Diego, in the US. He designed a set of coils that can perturb the magnetic configuration in such a way that you can stabilize the plasma edge. You can see here on the figure on the left, you can see that you see the ELMs, you see the envelope of the ELMs, it's written there, ELM amplitude. You see the envelope of the ELMs. Each of those vertical lines within the envelope is one ELM. So you can see that these ELMs occur in a kilohertz range. So you get about 1,000 bursts of energy per second. And when they switch on the coil currents, you see there, it's about 1.5 seconds. You switch on the coil currents, and then at some point around 2.3, for example, you see the ELMs disappearing, and then they disappear quite a while until you switch off the I coil currents. And then once you switch off, the ELMs come back much more stronger now because they were suppressed. So you accumulated their energy inside the plasma. But these coils have the capability of stabilizing the plasma. The problem is our models, the physical models, they are out by a factor of, not a factor of 50% or 70%, they are out by a factor 3 sometimes. So we don't know exactly what is the mechanism of stabilization of these instabilities when you perturb the plasma with magnetic fields generated by this set of coils that we call RMP coils. And the idea behind TCABR is to install a large number of coils so that we have extreme scenarios. So scenarios in which you could create, it's a machine that you can create so extreme scenarios in which the physics that we are missing, they appear more visibly. It becomes more visible what we are missing. So we are going to install 108 coils inside the machine. We have here on the left a number of 6 coils going around the plasma like this. And then we have 18 sets of these 6 coils, which then leads to 108 coils. This is an image of how the machine is going to be after the upgrade. You can see here on the right the coils on the outer side of the machine. There is an inclined one in the bottom, then another one around each observation port, and then on the top another inclined one, and the other 3 are in the more center part of the machine. The mechanical design is already done. We finished, and we are testing all these designs. Just to give you an idea, the mechanical force that we expect in each of these coils is the same force. It's a force equivalent of a small car. So we are going to have strong forces here. So the supports must withstand these forces. Once we have everything installed, we are going to be able to produce perturbations that can rotate, perturbations with n equal 1 periodicity, n equal 2, n equal 3. These are harmonics that we can produce. We could make an n equal 1 rotating in one direction, and simultaneously we could have, let's say, an n equal 3 rotating in the other direction, toroidally. We could also have a perturbation rotating poloidally in this direction here. And you actually could combine a toroidal rotation with a poloidal rotation. And then you could have a perturbation that propagates helically around the torus, following the field lines. This will be the only machine in which these experiments can be done. And the perturbations will be rotated up to 1 kilohertz for sure, and we are still evaluating if we can go up to 10 kilohertz, because then we could study, for example, momentum transport in this machine. There are some issues with with operating in alternate current. For example, we get eddy currents in the coil casing, the casing that supports the strong forces. You can see there will be strong currents that leads to high heating of these components. So everything must be compatible with some quick or adiabatic heating of the whole structure. So the screws must be strong enough to support these thermal dilations. And we also get inducted or induction currents, eddy currents in the vacuum vessel. This is going to heat up the vacuum vessel sufficiently, because here we are talking about perhaps hundreds of kilowatts of power being dissipated in these structures here. And we are, as I said, we are designing and we are now testing these coils. This is the first prototype that we finished within our private partner FCA. We are doing everything in vacuum, because these coils will be, the impregnation is being done in vacuum conditions, because these coils will be installed within the vacuum vessel. We had to design the impregnation system because the coils must be impregnated not just in vacuum, but also in high temperature. And this is the coil after we remove it from the system. and we started to install a reduced set of coils in a replica of our vacuum vessel, just to see if the design will fit finally in the vacuum vessel. This is the internal coils, and this is the outer coils. We also have some research from in other areas. For example, in plasma control, we will be able to control the plasma and give it a different shape than just a circular shape. For example, we can create plasmas more triangular with what we call a positive triangularity. If we invert the triangle, we get this negative triangularity. We will be able to do plasmas with significantly high squareness. And it's important to study these configurations because there is, in principle, from a theoretical perspective, when you change the shape, you change the topology of the magnetic field lines. And you could, in principle, stabilize the ELMs just by shaping the plasma. And the squareness seems to have a strong impact on the stabilization of ELMs. And our machine will be basically one of the, probably the only machine that go up to squareness of 1. And we are going to have single null diverted plasmas, double null diverted plasmas. And when you bring this upper X point down on the top of the bottom X point, you get this other configuration, the snowflake diverter configuration. And we are going to be the third machine in the world capable of creating this configuration, the snowflake, and the only one that can produce a snowflake diverter and perturb it with RMP coils. No other machine can do that. Only TCABR will do that. And that's a way that we found to attract collaborations with colleagues from other institutions abroad, from US, Europe, China. Once you perturb the plasma, for example, in the upper figure, it's a single null. In the bottom figure, it's a snowflake. You get a zoo of behavior of the manifolds that you can calculate and test, because we are going to have a camera looking down and measuring these lobes that appear. And this is a way that we can compare with simulations and study what is missing in the physics and in the numerical codes that we have. Just to finish, let me mention now about the upgrade of the Nova UFIS. We are going to install, this is very quickly, I know I'm close to my time. We are going to install at the bottom of the machine 2 plasma guns, 2 local helicity injectors, and you can see that you drive a helical current going up, and when the current driven along this helical path, when the current is high enough, strong enough, you get the filaments to interact, and you can get them to touch and reconnect, and then you get a ring of current going inside, and you can start populating and creating a toroidal plasma by populating this inner part with rings that gets created every time a filament touches the other, a turn touches the neighbor turn. And that's how we are going to increase the pulse length from 120 milliseconds up to 2 seconds, because we are going to start up the plasma with this system and get plasma currents up to 30 or 40 kiloamps. And then we can use our ohmic system to drive current. But now, since the plasma is already preheated, we don't use the flux in the ohmic system to do the breakdown and current ramp up while the plasma is cold. The plasma here now will be already somewhat hot enough so that you can now use the ohmic flux only to prolongate the discharge. And with that, we can achieve up to preliminary calculations show that we can go up to 2 seconds if we do that. As a summary here, I would like to finish just to bring attention to a few issues that I mentioned. We are going to pursue a set of research fronts in the upgrade of TCABR. For example, we are installing a set of RMP coils inside the vacuum vessel. All the coils are being powered independently. We are going to install graphite tiles to protect everything inside. We are developing localized helicity injection systems through these plasma guns that we are going to install in the bottom. And of course, we have to install some wall conditioning in the machine to prepare the machine for the experiments. We are also developing a digital plasma control system, and the power supplies, of course, not only for plasma control, but also for the RMP coils. Plasma diagnostics is something that we are also doing. I didn't mention here because of the time, but there is a set of diagnostics that we are planning to design and build. And as I mentioned, TCABR, now the upgrade, is being used as a platform to train a new generation of physicists and engineers. And this could be also used for colleagues in Latin America, because we could use this facility, either the TCABR upgrade or the new machine that we plan to design, as a platform for each of us in Latin America to train our new generation of plasma physicists and engage in this new race for fusion. So I think I got my time, so I prefer to stop here. And Julio, thank you very much again for the invitation. It's always a pleasure.
Good. Well, thank you very much. So, thank you, Gustavo, for such a comprehensive presentation in such a short time. ¿Hay alguna pregunta o algún comentario que quieran hacer?
Hi, Gustavo. This is Julio Martinel. I have a question regarding what you had been done in TCABR previously. You had a long program researching the heating with Alfvén waves in that machine. So I wonder if there is some plans of continuing with that, or that's something that has not been considered.
No, actually not, because we already removed the antennas from inside the machine, because there is no place anymore. You can see here, for example, in this image here, let me say, take another one. Here, for example. As you can see here, we have all these 108 coils, and we have also graphite tiles, and there is not space anymore in the machine. Actually, there is not almost space for the plasma anymore. We are installing so many things inside that the plasma got somewhat reduced, and we had to stop putting things inside, otherwise we wouldn't have plasma anymore. But the space now is very limited. For example, the plasma major radius today, in the today machine, the way that is today, was 18 centimeters, and we have to shrink it to 16 centimeters or 15. Getting plasmas with minor radius smaller than that, then it starts to become too small plasma, and we didn't want to. First of all, if we want to study ELMs, we have to make sure that we are going to get ELMs in the machine, in the plasma. So if we reduce more the plasma, then we would not get ELMs, and since we do not have additional heating only ohmic heating. We have to make sure that the ohmic power is enough to have a transition from L to H mode. And with a smaller plasma, we might not get into H mode and not get ELMs, and then the RMP coils become useless. So that was an issue also.
Okay. Okay, thank you.
¿Alguna otra pregunta? Sí.
Okay. Thanks again for the amazing talk. I'm really happy to hear about all the bright future of the Brazilian program. But my question is about, what is your approach about preparing the next generation of scientists and engineers, and what is the approach on attracting new talent to this program?
Right now, basically, actually it took me 3 years to let's say, to bring awareness among the students in Brazil. For example, I spent 3 years going to universities, giving talks, explaining them the importance of pursuing a career in nuclear fusion. And also, of course, if there is no scholarships, the students would not jump in, of course. And one important ingredient, especially in Sao Paulo, is that we have the State Research Foundation, which is the FAPESP. And through FAPESP, we were able to give these scholarships dedicated to fusion. And today in the laboratory, all the work here is done by students. We are only 2 professors. It's me and Professor Elder. Professor Galvão is retired. So only 2 professors, and we have 35 students working on the upgrade. And of course, we have support from colleagues from the engineering school of the University of Sao Paulo. So I had to spend also 2 years inviting other professors from, let's say, electrical engineer for the plasma control, electrical engineer for the power supplies. I had to invite people from the materials for the graphite part, graphite tiles. I had to attract people from the vacuum part, and all these different packages of the upgrade, I had to look for people interested in academia, professors that agreed to jump in the project, and each of these professors now they lead a different part of the upgrade, and those 35 students, they belong to these different groups. And that's how only 2 professors in plasma physics can do a modernization, because we have the support from professors from other areas, mainly from engineering, mechanical engineering, for example. All these coils here were designed by the colleagues from the mechanical engineering department from the University of Sao Paulo. So that's how we are building. And we also have programs to send students abroad. For example, today we have 2 postdocs in, one postdoc in Switzerland, 1 PhD student in Switzerland. We have 2 master students in France. We have another PhD student in Germany. 1 PhD student went to China, to Chengdu, and just returned. And we are sending these people abroad so that they can learn new technologies and come back and help us in our program. So it's a long-term story. It started 5-6 years ago, and we are now seeing the results after these 5 years. But we have to start it at some point. And if you guys, for example, in Mexico, for the students that are hearing now, for example, if the students think they want to pursue a career in nuclear fusion, they could look for a professor here, there in your university that would like to collaborate with us. And for sure, we are going to find somehow a way to collaborate. It could be through simulations. We have the codes for the simulations. We can provide the facilities where to run the simulations for magnetohydrodynamics, for example. We are also developing the codes that if you guys would like to contribute, we are developing codes for plasma startup, for example, and other kinds of codes. So there are plenty of space for collaboration here, and we are very open for that. So if the students that are hearing, they think they want to work on fusion, just look for Professor Julio Herrera and Julio, the two Julios. and for sure, we can find a way to collaborate.
Mm-hmm. That's a great answer. I should also point out that it's very important for Brazil to have an indigenous program so that they can attract the students back to Brazil. Yeah. Else they would just stay abroad. They would just stay abroad. Mm-hmm.
Yeah.
A general question: what is roughly the budget for fusion in Brazil?
For the upgrade,
or at least at Sao Paulo.
Yeah, for the upgrade, we have 20 million reais, our currency. It means, let's say, $4 to $5 million for the upgrade. And we are going to receive another amount for finishing the upgrade. And for the national laboratory, just the building, we are talking about 120 million for building the lab, and we do not have initiated the conversations, the negotiations about the future machine. We are going to do that once we get into the middle of the building done. So we are trying to do one step by step.
Mm-hmm. Well, thank you very much. If there is, si no hay alguna otra pregunta, then we thank Gustavo again. Thank you very much.
Thank you, Julio.
We appreciate your effort, and have a good time at Vienna.
Thank you. Bye-bye.
So long. Bueno, entonces nos vemos a las 11:55.